Okay, we're going to look at Galilean relativity and center of mass in this video. 14, what are the Galilean transformation equations 6.4 and 6.5 used for? Well, this is what they look like. Okay, showing that the time in two different reference frames is equal to time. They're the same, they're equal. Reference frame B and A, okay? And then this is the first equation. The second one is the position of an event in B reference frame is equal to the position of an event in one reference frame, in the A reference frame, a different one from that one, minus the velocity of B relative to A times the time over which you observe that event. Okay, these are called the Galilean transformation equations, and they allow us to relate observations made in different reference frames. They relate observations made in different reference frames. Okay, so make sure you go back and you read up on this. Okay, 15. Suppose observers C and D both measure a train's velocity. Okay, they measure a train's velocity but from different inertial reference frames. Okay, so you've got a train moving, and you've got, say, C looking at this, and then you've got D, who could also be moving at some speed, also looking at that. Okay, and they're measured from different inertial reference frames, so two different reference frames. C reports a velocity, so C looks at the train and says, oh, it's going at t in my reference frame. It's going at velocity vct, which is a velocity of the train in C's reference frame. And D says, oh, it's going at a certain velocity in my reference frame. What other information must C have in order to determine whether or not D's measurement is accurate? Again, we need to use the Galilean relativity equations. And basically what it says is the velocity of the train in C is equal to the relative velocity between the two reference frames, C and D, plus v dt. So we've got vct, we've got v dt, but how we relate them is we need this relative velocity between the two reference frames. Okay? Alright, next, 16. Center of mass. How does an object's inertia differ when measured in two different inertial reference frames? Well, it should just be the same. Okay? The inertia is the same in all reference frames. So, same. They're the same. There should be no difference. 18. Let's just look at 18. In an isolated system that contains moving parts, how does the system's center of mass move? Well, remember, we spoke about it when I was talking about the zero momentum reference frame. That even if you've got moving parts, okay, going at different velocities, okay, and as long as the system is isolated, it means that the center of mass, the velocity of the center of mass will not change. Even though these guys are moving, even though it has many moving parts, even if they collide, even if they bounce off each other, even if they have an inelastic collision, whatever, if it's elastic, inelastic, totally inelastic, As long as we have an isolated system, it means that there's no momentum transfer across the boundary. No momentum across the boundary. And if there's no momentum across the boundary, it means that the center of mass, the velocity of the center of mass remains constant. Whereas, so that means that your P of the system is constant, right? Because the V, this is the V of the system. Because the velocity of the system is constant, your momentum of the system is constant. But if you've got momentum transfer across the boundary, then it's going to change the momentum of the system, which means the velocity of the system would have changed. All right, where are we now? Okay, 19. What is the momentum of a system of objects as measured by someone moving along with the center of mass of the system? Okay, I've said this multiple times now. If you're moving at the velocity of the center of mass, it means that you're moving at the velocity of the zero momentum reference frame. You're moving at the velocity of the system. So if you're moving at the velocity of the zero momentum reference frame, then you measure a momentum of the system which is 0. Okay? Alright. Make sure you understand those. Cheers.